My name is Avi Paulson, and I'm an assistant professor of mathematics at Virginia Tech. Welcome to this first part of a series of videos where we'll explore Fourier series with the lens of linear algebra. Fourier series are important because they give us an alternative view on the world around us. They're part of a bigger field called Fourier analysis that has seen tremendous success with applications, ranging from compression algorithms to understanding the equations that describe the world around us. In this first part, we will review the concepts of inner products and norms from linear algebra, but with a point of view of analysis. In the second part, we'll use the concept of inner products to explore orthogonality. The highlight of this series is part 3, where we will view Fourier series as best approximations. Finally, in part 4, we'll introduce the tools that are necessary to explore the convergence of Fourier series. Now, the objective here in part 1 is for you to be able to prove theorems by applying the definitions and properties of inner products and norms. Along the way, I'll leave plenty of open questions or partial calculations, so please make sure that you fill in all the steps where necessary. But enough of setup, let's go ahead and do some math. We start with a vector space. So in order to define a vector space, you need objects, you need the vectors themselves, and then you need scalars. You need to be able to define addition and multiplication, that is to be precise, addition of vectors, and scaling of vectors, that is multiplication between scalars and vectors. In addition, you need a whole bunch of axioms. Now I'm going to quickly flash the axioms. There are 8 of them here in front of us. But the good news is that we'll be working with very concrete objects that you're familiar with, such as functions or vectors in the plane or 3D. So these axioms just describe all the tools and calculations that you're used to taking for granted. So I'm not going to focus on these, just going to click them off the screen and rather go straight to examples. Now, when you think of vectors, you may mainly think of vectors in the plane or 3D. But our goal in this sequence of videos is to look more at vector spaces of functions. So here are a couple of examples of vector spaces of functions. First example here are the continuous functions on a close bounded interval between a and b, or the n times differentiable, continuously differentiable functions on an interval. Now, the scalars that you're used to using are probably real numbers. That is, in the plane, you scale a vector, that is, you just multiply with a number. But for the purposes of this video, I want to set things up with complex numbers. You could do everything in this video just with real numbers. And if you're not familiar with complex numbers, you could just work through everything and substitute complex numbers for real numbers. But for those of you that have seen complex numbers, let me just recap that a complex number x plus iy, where I is the unit imaginary number that fulfills I squared equals minus 1. Now, clearly no real number can have that property, which is why it's an imaginary number. Now, you can visualize a number like x plus iy in the plane, in the complex plane, where x is the real part and y is the imaginary part. Now, this looks very similar to a vector in the plane that you can denote with x, y, and even the magnitude of a complex number and a vector are given the same way. However, let me warn you that these two are different objects, and even though they look so similar, then you get a lot richer structure with complex numbers, which is why you will find classes on complex analysis. Highly encourage you to take those kind of classes if you have the opportunity. They present some of the most beautiful theorems within analysis. Now, to continue a little bit with complex numbers, then I wanted to introduce the conjugate of a complex number. You can visualize this conjugate by mirroring a complex number by the real axis. That is, you just go down beneath the real axis. Now, the nice thing about conjugates is that they distribute nicely, both over addition and multiplication. So why do we need conjugates? Well, when you have real numbers, and you multiply a real number by itself, be it positive or negative, out comes the magnitude of the number squared. For complex numbers, that's not the case. So the conjugate is needed in order to multiply a number and get the magnitude of the number squared. So that is one reason why you might be interested in a conjugate. Another thing I wanted to mention very briefly is Euler's formula that connects the complex exponential with our favorite trig functions cosine and sine. That is, you can visualize a complex exponential as lying on the unit circle because the magnitude clearly is 1. But this connection is important because when we move to Fourier series, we'll see a lot of cosines and sines. And even though in this sequence of videos I'll present to you real Fourier series, then one can actually present everything with complex exponentials. And that is a fun exercise for you to do. Now, let's look at the dot product. So from the plane, 3D, or any higher dimensional Euclidean space, you may recall how to find the dot product of two vectors. You just take corresponding coordinates, multiply them, and add everything up. Now, this concept was important because it connected vectors to the angle between them. That is, to be precise, the dot product between two vectors gives you the product of the magnitudes times cosine of the angle between them. Further, the dot product connects to the usual length that you're used to in Euclidean space. That is, the magnitude of a vector equals the square root of the dot product of the two. Now, I said that we wanted to move away from examples like Euclidean space and move towards vector spaces of functions. So one of the questions is, what does it even mean to find the angle between, say, functions? What is the analog of the dot product? Now, in order to see that, we need to review the concept of inner products from linear algebra. So from now on, my vector spaces are always going to have the scalars, which are either the real numbers or complex numbers. Nothing more exotic than that. Now, then one can define an inner product as a map that takes in two vectors and outputs either a real number or complex number, depending on what scalars you're working with. In addition, it has to satisfy some important properties. So when you take the properties of the dot product from the Euclidean space and you distill the most important ingredients, then one can boil it down to three important ones. The first one is that the inner product is positive definite. That is, when you take the inner product of an element with itself, out comes something that is non-negative, and in particular you only get 0 if your input was the 0 vector. Secondly, there needs to be some sort of symmetry. In the Euclidean space, you're used to that it doesn't matter which order you dot two vectors in. Now, if you allow complex numbers as scalars, then you have to be a little bit careful. We don't just want symmetry, that is, that it doesn't matter in which order you evaluate them. One has to have conjugate symmetry. That is, if you switch the order, it introduces a conjugate over the inner product. Now, thirdly, we have linearity in the first position of the inner product. Now I wonder what that does for the second position. What do you think? Be careful when you calculate that you have to use the second property if you switch the position of the first and the second. Now, for some examples of inner products, then we already talked about the inner product being a generalization of the dot product. So clearly the dot product is still an example. But if you move to the complex spaces, well, then you can set up something very similar to the dot product. That is, if you have two vectors filled with complex numbers, then you can define an inner product by just taking the corresponding coordinates, multiplying them. But here we have to be careful. The second coordinate has to be conjugated. Now, if you think about it in terms of just a single complex number, then remember that a complex number times itself is generally not the magnitude of the number squared. You need to conjugate. That explains why you have the conjugate on that second part. Okay? So that is one way of defining an inner product on an n-dimensional complex plane. Now, secondly, we have an example here of an inner product for the continuous function on the interval a to b. Remember that an integral is just a fancy sum. See, for the complex numbers, you just added things up. For functions, you essentially add up things too, except because things are in a continuous setting, you're integrating. So it's kind of the same concept. And just as in the complex world you had to put conjugates on the second coordinates, then similarly for functions you need to put a conjugate on the second function. So these are some examples of inner products. Now what about norms? Again, our vector space has scalars which are the real numbers or complex numbers, and one can boil the concept of a norm down to three conditions. So a norm is a function that takes in a vector and spits out somehow its magnitude, so it spits out a real number. And what we want is that a norm of a vector is always non-negative, and in particular that the norm is only 0 if you input the 0 vector. Secondly, you want to be able to scale vectors, and you want the norm, the measure of how large they are, to scale with the number that you use to scale the vector, which is the second condition. The third condition one can interpret as the triangle inequality. If you're working with vectors in the Euclidean space, then it is quite precisely the triangle inequality, and in a general context, even for functions, we will still call this the triangle inequality. That is, the hypotenuse is in magnitude no more than the sum of the two other sides. Now, if you are lucky enough to be in a vector space that has an inner product, often called an inner product space, one can define a function that turns out to be a norm by taking the square root of the inner product of a vector with itself. Now, it is quick to see that this fulfills the first two conditions of a norm, and certainly is a mapping on vectors and does spit out a real number. The only question is, does this fulfill the triangle inequality? That is not obvious from the beginning. Now, the tool to see that the triangle inequality is fulfilled is called the Cauchy-Schwarz inequality. A colleague of mine once told me that all good proofs in analysis have either the Cauchy-Schwarz inequality or integration by parts. So this is one of the most important tools in the toolbox of an analyst. So what does the Cauchy-Schwarz inequality say? It says that the magnitude of an inner product of two vectors is no more than the multiple of the magnitudes of the vectors. Now, how would you prove something like this? Well, it requires you to use the definitions and properties of norms and inner products. And I'll give you a little hint. Look at this quantity here, f minus alpha g. Look at the magnitude that squared. Now, why would you look at the magnitude squared? It's because you can relate the magnitude squared to the inner product. Write this out. Expand. Now, that does not completely conclude the proof, because you need a very clever, creative, if you wish, choice of the scalar alpha. But remember, you can choose it however you want. I will leave this as an exercise for you. Now, to see why this is enough, let's look at the triangle inequality here. Let's look at the left-hand side of the triangle inequality, the magnitude of f plus g squared. Now, looking at magnitude squared is also a good idea because it allows you to use the inner product. Remember, the inner product of a vector with itself gives you the norm squared. Now, when you expand this out and make sure that you, on paper, write down all these calculations, that you use the properties and definitions properly, we end up with the second line here, which I claim can then be bounded using the Cauchy-Schwarz inequality. Now, how did I do that? Make sure that you got everything covered there. Now, in the last line, we just see that we have a magnitude squared, something squared, and we can take square roots, and out comes the triangle inequality. So in this video, as a summary, our objective was to be able to prove theorems by applying the definitions and properties of inner products and norms. So the highlight, sort of the punchline of this video, is that vector spaces that are endowed with inner products, and thus have associated norms, are somehow special. And in the next part, we will use the definition of an inner product to explore orthogonality. Without the concept of an inner product, that would be impossible. And in terms of the calculations we did, then we used the definition and properties of inner products and norms to prove the Cauchy-Schwarz inequality, although I left some explorations open for you to fill in the gaps where needed. This concludes our part 1, and next time we'll move to part 2 of this series, where we'll explore orthogonality using the concept of inner products.